All right, folks, so happy Friday. I hope everyone enjoys the nice weather that we have this weekend. All right, so we're going to get started here. We're starting chapter 7 today. So we're taking the ideas that we learned about the electronic structure of our atoms, what it means to, putting electrons within our electron configurations and those orbitals. We're basically looking at the consequences of that. Right, within chapter 7, because it's electrons, specifically valence electrons, that dictate the chemical properties that we see. So we're going to go into a lot of detail about that. So big ideas for this chapter: electron configurations. You should be able to, if I give you any element, just using the periodic table, you should be able to gather that electron configuration like that. All right. But before we get started, do you guys want to hear about my tractor? All right. Okay. But, I can't talk about my tractor unless I make it about chemistry and make it a story. All right. So I told you, at the beginning of the term, I look around life and think and just ask questions. So one question was, why do diesel engines only roll coal? I was in the car with my husband, and he drives a truck. And I said something like, oh, you should, so like some guy cut us off and then started going slow. And I was like, oh, you should roll coal on him. And he was like, no, Lisa, I can't roll coal. I have a regular engine, or use regular gasoline. I'm like, in my head, I'm like, why? Like, those things don't make sense. What? Yeah? Oh, it's that. See the truck with the black smoke? Yeah, have you ever been on the highway and then you see the big plume of black smoke? What? Yes, I hate them, and I'll show you for several reasons why we hate those people. No, I don't hate them, but we live in Ohio, right? You've seen people roll coal. Has everyone seen that, all right? So I will talk about chemically why it's annoying, okay? And so my husband very gently corrected me and said, no, only diesel engines can roll coal, regular engines can't. So I did the research for you, all right? So we just bought a tractor, and it's my first diesel engine, so yes, it can roll coal, but, okay. But my little car, all right, my little 2010 Toyota Corolla cannot roll coal. All right, so all normal gasoline unleaded cars cannot roll coal. And the reasoning is that diesel engines are fuel metered while regular cars are air metered. And I'll explain to you what that means in the context of a combustion reaction, because that's what goes on in our vehicles, right? Okay, so here's the combustion reaction for octane. So there's a lot of different hydrocarbons in gasoline, but when we think of gasoline, we think of octane. So, you see the balanced chemical formula for the complete combustion of octane. And so what I mean by complete combustion, it means that we completely oxidize carbon that's in octane to carbon's most oxidized form, which is CO2. That's its most oxidized form. So when we think about the products that you see for the complete combustion of octane, CO2 and water, does that look like anything? Like if you see that on a tailpipe of a car, do you see anything? No, CO2 is just a gas. Water vapor just looks like vapor, right? So typical cars, you only see like a white plume kind of come out. That's complete combustion of octane, and you get a lot of energy when that occurs, all right? You get a lot. Where's my stupid pen? Oh no, my pen's not clicking. Complete combustion of octane, you get a lot of energy back, all right? You see here, for every 1 mole of octane that you burn, you get about 500 kilojoules of energy out as energy. In order for complete combustion of octane to occur, octane has to be the limiting reactant. There has to be an excess of oxygen. All right, so that's what happens in air-metered cars. When you step on your gas pedal, your accelerator, you're sending more air through your engine to push combustion reactions to occur. So in typical cars, oxygen is always the excess reactant. So you always have complete combustion occurring. It's different in diesel engines because when you hit the throttle on a diesel engine, you are sending more fuel through your engine. And that's what people call running lean, meaning that you're putting a lot of fuel into your pistons. And so what happens is when you have a ton of fuel in your piston and it's burning, you have incomplete combustion occurring, that you have a lot of fuel, but not a lot of air. All right, so now in this scenario, oxygen is your limiting reactant. So you don't completely oxidize carbon, the carbon atom here. So you make some carbon monoxide and you make carbon solid. So it's carbon in its zero oxidation state. And so that carbon solid is what you're seeing out the flue pipe of your vehicles. Yeah. There's a couple reasons why this is worse, all right? And that's this energy level diagram, all right? Where we have reactants. We're starting with gasoline and air. And think about our product. So in complete combustion, your delta H is actually much, much larger, more negative. So you are getting more energy per octane unit. All right, so you can go further on less gasoline. But if you are rolling coal, oftentimes doing incomplete combustion, you get a smaller delta H. You don't get as much energy out, all right? So you'll have to burn up more gasoline in order to go to the same amount of distance. So you think about it energetically. If you are constantly rolling coal or running lean, you are burning, you're not taking advantage of all of that energy that octane has. All right, and so you get less energy out. So for those reasons, it's bad for the environment and because you're putting particulates of carbon in the air. Does that answer your question? What? What? No, we own a truck because we have to pull our boat. No. No, I can't. No, so I can't tow a trailer with my Toyota. No, but see, that's the misconception that all trucks can roll coal. That's not true. We drive a regular gasoline-powered, like unleaded fuel truck that does not roll coal. It's only diesel engines can roll coal because it is fuel metered, not air metered. Okay, so this all has to do with limiting reactants, okay, combustion reactions, and enthalpy, which we learned about. Okay, was that interesting? Okay, so now you know. Okay, so let's get started. Any questions about that? Okay, but I will say that diesel, you get more energy output per liter, per like amount volume of gasoline in that case. So if you are running, with the correct air fuel mixture, you will get more gas mileage off of a diesel engine as long as you aren't deliberately rolling coal. So if you see people roll coal on the highway, just know that they are not getting good fuel economy. All right, and they're doing bad for the earth. Yeah, okay. All right, so let's get started. Okay, so chapter 7, properties of our elements. So we're going to be taking a deeper look at our periodic table, how it came to be, why the elements are where they are, and some of the trends that we see with our elements. So we got to talk about these guys who came up with the basis of our modern periodic table. So what's really interesting about these two gentlemen is that they came up with the order of the periodic table before we, started learning about all the subatomic particles and all of that we talked about last chapter. So the idea of the periodic table and ordering it to close to where it is in modern day actually started in the early 1860s. All right, so this was before the discovery of subatomic particles. So these two guys independently came up with the same conclusion, that they both kind of came up with similar ideas of what the periodic table should look like, but we only remember one of them. Mendeleev. I feel like most people, if you do know anything about chemistry or the periodic table, Mendeleev probably rings a bell more than the other guy. And I'll tell you why we remember Mendeleev and not the other guy. And that's because Mendeleev, so they built these tables in the 1860s. So we didn't actually know all of the elements then. All right, so the reason we remember Mendeleev is not only did he get it correct, like how the elements arrange themselves, but he left blanks in the periodic table where elements should have been. So he knew that like silicon, or I guess right under silicon, germanium, that element was missing from, we didn't know what germanium was yet, so he deliberately left a blank in his periodic table and even predicted what those properties of that unknown element should be. And that's why we remember Mendeleev and not the other guy, because he took all the puzzle pieces that he had and put them together to make them fit. But Mendeleev was a little bit smarter and knew, hey, we're actually missing a puzzle piece, so I'm gonna leave some space for it because I know that that piece is missing. And I think he even suggested where to find that element, because he was able to use the idea of periodicity and periodic law, that we see the same types of behaviors and chemical properties over and over. And so this is, this is what Mendeleev predicted about germanium. So this is the element in the same group as silicon, so just one element, one period down in the same group. So this was his predictions, and then finally, a decade or so later, they actually did discover silicon, and his predictions were very spot on. And he was able to make these predictions because he understood group chemistry, that we see the same types of properties over and over. All right, and so it kind of looks like this. All right, so, thinking about chemical history is, and talking about it is really tough, because we always apply our own biases. We live in modern day. So answering questions that have to do about history and why chemists did things a certain way, it's really tough because we always apply our own biases. So this question, this is, Mendeleev's periodic table. This is how he wrote it, and then of course we made it more visually appealing later, but it's all there. What information do you think Mendeleev used to group these elements? A, B, C, or D? Take a second, think about it, talk about it with someone else. Keep in mind what I just said 30 seconds ago. What do you think? A, B, C, or D? All right, does anyone think C? Does anyone think C? Protons didn't exist then, or we didn't know what protons were then. Yes, we do order elements in order of their, the number of protons, their atomic numbers, but they didn't know what they were. When did we discover protons? I don't know, the 1911 or something like that. So we didn't know what they were yet. So to us, they didn't even exist. So yes, again, we're looking at history through the lens of modern chemists, unfortunately. So it's not C. So that means it can't be what as well? Or D and A, yes. Yeah, so A, it can't be A either because we didn't even know what an electron was. All right, so the correct answer here is B. You all thought this was an easy question. Yeah, but it's not. It's B. Because, again, we didn't know what these were at the time. Okay, so modern periodic tables. So Mendeleev was the one who set us up for success, and now we, thanks to him, have this beautiful looking periodic table that tells us a lot of information, not just about the order of the elements, their weights, but it tells us a little bit about their valence electrons and electron configurations, just based upon where those elements are sitting on the periodic table. So what we see here with our modern day periodic table, why we make it like this, is because we want to order our elements in terms of their reactivity, and really when it comes down to it, it's ordered in terms of the arrangement of their electrons, specifically valence electrons. And we talked about this at the end of chapter 6, right? For a lot of our main group elements, our S and P elements, we can predict the number of valence electrons based upon its group number. And that's what Mendeleev was able to do. And really, our modern day, so our groups, we have our groups based upon valence electrons, our group numbers, but also our rows that we see or our periods reflect our n quantum number. As we go down our periodic table, that n value increases. So for hydrogen, that's an n of 1, but if we go to something like potassium, that's an n of 4, because potassium is a 4s element that we have, or the fourth row down, and that highest energy electron is in an S type orbital within there. So, yeah, all right, so taking what Mendeleev did, we are able to put together a periodic table. We have our rows, so I just said this, that the rows represent, our principal quantum number, their n, or our shell around our atom. So as we go down our periodic table, our atoms do get bigger because the n value increases. And higher n values mean that we have higher energy electrons. They're, on average, further away from the nucleus. Then our vertical columns represent our groups that we've talked about. We've already utilized group numbers before in chapter 2 when we predicted charges of ionic metals and non-metal anions. We already have used group numbers to predict those charges of cations and anions. And so what that group number represents is the number of valence electrons in that group. Okay, so we do know that the periodic table is ordered in order of increasing number of protons. So if you just keep going across the periodic table, we see that all of the elements increase one proton with one element. You'd think that like back then they would order it in terms of mass of the elements, but they didn't, or they tried to but realized that it didn't work, because if we actually look at the molar masses of these elements, some of them kind of swap out of order. Right? Didn't we already we looked at some of them? Which ones are like weird, where it doesn't increase? Crap, now I can't find one. Can someone find one where the masses, the atomic masses, don't exactly increase in order? I can't find one. I should have written this. Te and I, tellurium and iodine. Very good, yes. So 52 and 53, that you'd think that you increase a proton, the mass would increase, but it doesn't. So good thing that they didn't go by masses. Thank you, whoever said that. Thank you. So we do know that the elements increase in terms of number of protons. So how did they figure this out? So we're going to talk about light again. So this is how they figured out the order of the elements or atomic numbers. They utilized light here. So with this experiment, how we figured out atomic numbers and why that is related to number of protons is with Henry Moseley's experiment, where he bombarded different elements or atoms of different elements with a lot of energy. And he saw that elements emitted a unique set of frequencies of X-rays, so they all emitted light. And so what he inspected was the energy of the light emitted and was able to relate that energy of light emitted to the number of protons to the nucleus. So this has to do with potential energy again. And so I might have to draw our favorite diagram. And so yes, each element produced a unique frequency of X-ray. And so the observation was that as the atomic mass of the element increases, the frequency of emitted light also increases. And I'll explain why. It has to do with the number of protons in the nucleus. More protons, more attractions that electrons have to that nucleus. Okay, yeah, so he arranged those frequencies in order of whole numbers that he called atomic numbers. So you can kind of see that here. On our x-axis here is atomic number, and on the y-axis, that is the energy or frequency of light emitted by that specific element. And so he basically just drew a line here and said, more protons or higher atomic number, the higher frequency of light X-ray that was emitted. So he observed these high energy X-rays. So what that implies is that when an electron is emitted, when a photon is emitted, well, let's think about it. When a photon is emitted, back to chapter 6, is an electron on the atom falling, or is it going up? Falling. Okay, so if we have a high energy X-ray, does it make a small fall or a big fall? Big fall. Okay, great. So if all of these electrons are falling to an n equals 1, so the lowest energy level, in order to have a really big fall, if that n equals 1 energy level is very stabilized, a very negative number, then we have a big fall. And so that's what he deduced here. And that happens when there's more electrons in the nucleus. So that's what you kind of see here. Higher energy photons emitted implies a more negative n equals 1 energy level. And it all has to do with potential energy. So let's think about it, about the difference of an n equals 1 energy level. Consider a hydrogen and a helium atom. All right, let's just look at one electron around a hydrogen. Oh, I don't want that color. Let's do this color. All right, so there's my electron on a hydrogen atom. There it is on a helium atom. Which electron on a hydrogen or this helium atom experiences more attraction? The hydrogen or the helium? Helium. Why? Its Q1 is +2 versus +1. So that's right. If we compare the distance of this n equals 1 for both of these, which electron is closer to the nucleus? A electron on helium or on hydrogen? Which would be closer? Yeah, on helium, because it is more attracted to it. It's more attracted to a +2 nucleus. All right? So that's our n equals 1. So I'm going to show you the next slide here. So what I'm basically doing here, is applying our potential energy equation, where potential energy is basically equal to Q1 times Q2 over distance. So Q2 on helium is a larger positive number. That electron is more attracted to it. So what does that mean when an atom has more protons and that n equals 1 electron is more attracted? It means that that n equals 1 energy level is further down. So if we have an electron that's falling, it's going to fall further for heavier atoms, atoms with more protons. Do we see where I went there? This is a hard thing to get your head around. But the big idea, the observation was that heavier elements, so elements with more protons, emitted higher energy X-rays. And this is the reason. The more protons in your nucleus, the lower your n equals 1. Lower energy n equals 1 with more protons. So when we have an electron that's falling, let's say to n equals 3 to 1, we have that size drop. But then when we do the same thing for an atom with more electrons, we see that that change in the atom is larger for our multi-electron system. You see that my arrow is literally bigger, right? And the downward arrow means that a photon is emitted. So since my arrow for the multi-electron atom, so this could be like helium, for example, versus hydrogen, delta E atom, is larger for our multi-electron atom. That means that the energy of the photon that is emitted for our multi-electron atom will have more energy. Its wavelength will be shorter. Its frequency will be higher, because that multi-electron atom has more protons in its nucleus. Do we see that? More protons, lower n equals 1. So when we emit energy from falling electrons, they fall further, because essentially the pit where n equals 1 is just deeper. Okay. All right. Do we get that? We get that? So which element would emit a higher frequency X-ray? Cobalt or magnesium? Cobalt or magnesium? Cobalt. How do we get that? Its molar mass is larger, its atomic mass is larger, specifically because its number of protons, all right? So it's a very straightforward observation. More protons, higher frequency X-ray, but I think the explanation for it really kind of builds off of Chapter 5 and Chapter 6 material that we talked about in previous weeks. Okay, so there we go. All right, so talking more about electrons. So this section, I could talk an hour about effective nuclear charge. This is all about electrons, all right? We need to think about I hate saying that like electrons have feelings, but this is what we do have to think about. Chemical reactivity is not only described by what group elements are in, but it's also explained by the attraction that valence electrons have to the atom itself. And this is explained by effective nuclear charge. All right, so what is here? Many properties we observe depend on electron configuration, so meaning, what group elements are in. Also, it's dependent on how strongly those outermost electrons, those valence electrons, on an atom are attracted to the nucleus. So this is where effective nuclear charge comes from. So essentially what this is, so here's the equation for it. It's Z subscript EFF, which means effective nuclear charge, is equal to the charge of your nucleus minus a shielding factor. I need to talk about some analogies here, but let's just all pretend we are electrons, and you want to think about how is that outermost electron, what charge of the nucleus does that electron feel? So you have to think about what other electrons are in the way of you. So if we think about a hydrogen atom, and we already talked about a hydrogen atom before, hydrogen just has a positive nucleus, and there's only one electron, right? So if you were an electron on a hydrogen atom and you looked at the nucleus, what charge would you see? +1. But if there were other electrons in the way, you might not see the full +1 charge, okay? So building up to that. So that would be a shielding factor. So basically, this is the equation for effective nuclear charge. So that's Z effective nuclear charge. How we calculate it is, again, what this number indicates or represents is what charge a electron feels relative to the nucleus. The nucleus is positively charged, right? Okay, so pretend I'm the nucleus, all right? I'm the nucleus. Let's say I'm a positive, my favorite number is 51. I'm a positive 51 charge, okay? So if I'm standing right here, all the people in the front row, if you're looking at the nucleus, my charge is positive 51. What charge do you see? Positive 51. Okay, what about Shane? Remember, you're all electrons. I'm a positive 51 charge. You're an electron, but there's an electron in front of you. Okay, electrons are negatively charged, right? So what charge do you feel? Do you feel the whole positive 51 charge? There's a negative in front of you. So what net charge do you feel? +50, right? So 51, that is Z. I'm 51 because I have 51 protons. Okay, so Shane, he's an electron looking in, but there's an electron one electron shielding him from the full charge of my glory. All right? So the shielding factor in that example would be 1. All right, and so I can do it for many examples of people. So if we have, okay, the guy in the pink, right? Yeah, you. Okay, so I'm positive 51. You're an electron. How many electrons are in front of you? Okay, 3. So your shielding is 3. Your shielding is 3. So what charge do you feel? Wait, what number? 48. Yes, because Z is 51 and shielding S would be 3 in that case. So this is what we need to think about. Our valence electrons are on the outside of the atom. They're on the outside of the atom. So there's a lot of electrons between the outside and the inside of the nucleus. So we need to think about what are the core electrons shielding that outer electron from the full charge of the nucleus. Yes?
So if the valence electron can see through a window, if you will, like a thick photo, they can see all the way into the nucleus and there's no shielding factor?
So remember, do electrons, are they?
They're just kind of out there.
They are out there, but are they static? How do we represent electrons around a nucleus? I think that's a really good question.
They're moving within their fields, right? Because we can't be certain about
What do we call the field? If it's like zipping around a nucleus, orbital, right? So an electron is in an orbital, in a round-shaped orbital or a P-shaped or a D-shaped. So really, the electron is there all the time. It's in all of those places all at the same time because of the Heisenberg uncertainty principle. So you can't So yes, in my example, when I said like, you know, like there's one electron in front of you, that actually would never happen because electrons aren't static, like two particles that are trying to look through each other. Okay, I don't think I answered your question though. Yes, yes, if we keep going. So in general, the closer your electron is to the nucleus, the less the shielding is. Yeah, okay. Yes? Oh yeah, everything's based upon a potential energy.
Would the electrons behind, like the next energy level back, push it towards the nucleus?
So typically, okay, so let me do my analogy again. Okay. So Shane, I'm positive 51. What charge do you feel? 50. Do the electrons behind you affect what you see at all? Does that answer your question?
Well, I mean, the repulsion between the ones behind it still exists, right?
They do, but not as much as electrons that are closer. Okay, so there is repulsion within electrons in the same shell. So the folks that are actually sitting next to Shane will affect what charge that he sees, but not as much as electrons that are standing between me, the nucleus, and the electron that I am observing. Those are great questions. Yeah, okay, all right. And a lot of debate on which theory is the best theory. But for our purposes, if we just compare valence electrons and inner core electrons, it will explain the majority of the trends we see. We can look at really, really minute details. That's called Slater's rules, where we take into account electrons that are in the same energy level or, in the same energy level, but it doesn't affect effective nuclear charge as much. Okay, so there we go. I think I just said all the same things here. So the strategy for determining the effect of an atom is first, typically when I ask you questions of this, I'll give you the atom. I'll say like sodium. And I'll ask you what is the effective nuclear charge of a valence electron. So you would know that that's the highest energy electron. But I don't have to ask it that way. I could say, what is the Z effective of a electron, a 1s electron on a sodium atom? So I can ask you what Z effective is for any electron. So for example, a 1s electron on sodium. So you ask yourself, not sodium plus, sorry, just sodium. So you ask yourself, on a sodium atom, what is the charge of the proton, or of the nucleus? What's the charge on a sodium atom? Plus 11, okay? But a 1s electron, is that electron close to the nucleus or far away from the nucleus? Very close. So are there any electrons between the 1s electron and the nucleus? No, so shielding is actually 0 in that case. So you have to think about what electron we're talking about. If we're talking about a valence electron, yes, you have to consider the inner core, but for other electrons, you don't.
Your last sentence again, the part about the shielding and why it's
I'm not sure what that question. Let's just do some examples. We didn't actually do any calculations yet. All right. So so our strategy here: first, determine the charge of the nucleus. Then we need to determine the screening constant, depending on what electron we're looking at. So really, the simplest model, what we'll use in this class, because it can explain 99% of things, is we will consider our S, our screening constant, what is standing between the electron and the nucleus, how many other electrons are standing between. We will just consider them inner core electrons. So the best thing to do is just write out the whole electron configuration, identify what electron are we pretending to be and how many inner core electrons do you have. Okay, so we haven't done an example yet. And then you just do the subtraction and that's your Z effective. All right, so here's my example. So we'll look at sodium. Sodium has we already said, has 11 protons. That's its Z, right? So now we need to figure out S. And again, the best way to do it is just write out the full electron configuration. Sooner or later, you'll just be able to kind of look at the periodic table and figure it out. There's some trends there too. So within this, we are trying to figure out the Z effective or effective nuclear charge for a valence electron on sodium. So that means, well, first let's figure out what is the valence electron on sodium? It's the outermost, but specifically in the electron configuration, which electrons are the valence electrons? Yeah. Oh wait, that's not even right. That's not right. Wait. No, that's like super not right, Lisa. What do I need? Oh, I just need one more. I'm sorry. 3s1, thank you. That's not even right. Okay, very good. You guys keep me on my toes. Okay, now what is the valence electron on sodium? That 3s1 electron, yes. So we need to pretend we are a 3s electron, that we are in the third. If we think about it in a Bohr type model, we're in the third ring around the nucleus. That's the electron we are. We need to identify the inner core electron, all right? So that 3s electrons, that's our valence, okay? So what electrons are our inner core electrons? All these ones. Yeah, so these are our inner core. So if we want an equation to describe that, inner core electrons are all n values that are lower than the electron you're looking at. So in this case, the electron we're looking at is in a 3s orbital, so we will look at all n values that are less than 3. So that means 1 and 2. So for example, let's say we weren't doing this for a valence electron on sodium. Let's say we were doing it for a 2s electron on sodium. Then our inner core would only include 1s, for example, because 1 is less than 2. Okay, so, all right, so that's our inner core. So how many electrons are in our inner core? 10. So that means that S, our screening constant, is 10. Because 10 electrons in inner core. Oh, this isn't right because I didn't do it right. This is what happens when I write slides at midnight. Okay? I'm sorry, this isn't right. All right, so we didn't even calculate Z effective then. So if you put that in our equation, right, Z effective equals Z minus S, that means the effective nuclear charge is what for that valence electron? +1 for a valence electron on sodium. Because we got Z, that's just the charge of a sodium nucleus, and we got S, we had to write out the full electron configuration and identify how many electrons are in that inner core. Sorry that this slide is riddled with mistakes. Okay, so kind of another way to think about it, remember like my whole analogy, I'm the nucleus, all the people in front of you are electrons shielding you from my greatness. We can think about it in the same way with the solutions to our Schrodinger equation, our radial probability map, or radial probability graph. You can see on average, these 2s electrons are further from the nucleus than a 1s electron. So that means a 1s electron is much more likely to get in the way, all right, and shield the full positive charge of the nucleus from an outer electron, such as an electron in like a 2s or 2p orbital. You can see that in terms of where the electrons can be found most of the time. If you were an electron, you know, this distance away from the nucleus, these 1s electrons will shield you from the full charge of that nucleus. Okay, and then this graph shows kind of the nuances. What we are doing right here, just considering all inner core electrons shield 100%, isn't really true. There's a bunch of different simulations and different calculations you can do, such as Slater's rules, where you use like fractions of a charge depending on where that electron is. But in our case, saying a shielding of one, like for one, every inner core electron shields perfectly works fine. Because what we see here, these squiggly lines, okay, these ones, these are 3 different methods. Some of them are advanced, some of them are mediocre, like, you know, inner core electron shield effectively. These graphs look the same, don't they? All right, so this is just like with a bunch more math, we can get a little bit more precise here. But again, when we say inner core electron shield perfectly for one, that it works fine for us. So that's what we see here. If we're using advanced methods, it barely changes at all. Okay, so let's do some practice with effective nuclear charge. So remember the strategy. Get Z, figure out S, and then calculate Z effective. So for lithium, so let's write out its electron configuration correctly. Lithium, 1s2, 2s1. So we're going to calculate the Z effective for the valence electron, so the outermost electron for all of the examples. So the valence electron is basically the last electron that I draw. So in this case, for lithium, what is Z? 3. Then we need to identify what S is. So remember, we are the outermost electrons. We are a 2s electron. So you count how many electrons are standing between you and the nucleus. So in that case, it is only those 1s electrons. So S in this case is what? Shielding is what? 2. So Z effective is +1. Okay, let's do boron. So boron is just one element over, so 1s2, 2s2, wait, no, it's 2 over, sorry, 2s2, 2p1, right? Yes, okay. So Z in this case is what? 5. Shielding is what? Nope. Remember, so we are a valence electron. So we could be a 2s electron, a 2p electron, right? All of those are valence electrons. So we want to pick n values that are lower than 2. So that only includes the 1s electrons. So our shielding in this case is still 2. See that? I see some whispering. We don't like that. Remember the rule, all shielding electrons are lower n values, lower n values. We haven't, our valence electrons are still in n equals 2. Okay, let's keep going. Oxygen, 1s2, 2s2, 2p4, 4. Okay, Z is what? 8. Shielding S is 2. Yes, you got it right this time. Okay, so that means Z effective of a valence electron on oxygen is +6. So I should circle these. So what does all this mean? This means that an electron on lithium, a valence electron on lithium only feels a charge of, if it looks into the nucleus, it only feels a charge of a +1. But if we look at an oxygen atom, if we're a valence electron on an oxygen atom looking at the nucleus, because there's only 2 inner core electrons that are shielding it from the full charge of that oxygen nucleus, it feels an effective nuclear charge of +6. It is actually more attracted to the nucleus. Yeah? Nope. Nah. I will explain the answer to that at the end of the chapter. Do you want it now or can you wait? It's oxygen's a non-metal, so typically they will make bonds with themselves. They don't typically give up electrons like metals do. So instead they'll just make bonds with each other in order to fill their valence shells. Okay, yeah. So all right. Okay, one more. Sorry. So we didn't do neon. Neon is 1s2. 1s2, 2s2, 2p6. So Z on neon is 10, yeah, +10. Shielding is 2. So that means neon has a Z effective of 8. Okay, and so do you see any trend here of what Z effective is? It goes up as you go left to right across the periodic table. Are those numbers related to anything? The group number. Oh, yeah. Your question? Not so much Z effective, no. Yeah, I'll have to think about that. It has more to do with electron configurations. Yeah. Okay. Yes, so it is the group number. It is the group number. And we will see when we look at periodic trends, this isn't super intuitive, but lithium is larger than an oxygen atom. It's larger because the valence electrons are less attracted to the nucleus. That size in the same period, all right? Like if we go across lithium through neon, the atom sizes get smaller as you go left to right. That's not intuitive. It's not, right? Because the atoms, they're going up in mass, they're going up in atomic number, but they get smaller. Z effective explains why they get smaller. Weird. Okay, and that'll come up in a slide in a little bit. Okay, one last thing. So that's across the periodic table. So we have neon. If we go one element past neon, sodium. Okay, sodium. So without even thinking, what is the Z effective of sodium? 1. It is 1 because sodium is in group 1. Or you can think sodium is like a 3s electron, right? And its inner core will be a neon, the neon core. And so it's 11 minus 10. Magnesium will have a Z effective of +2. Calcium will have a Z effective of +2. Yeah, so I'm filling out this, okay? So now we're going to look at trends going down a periodic table. So we just got magnesium has a Z effective of +2, right? Because it's in group 2. So calcium has a Z effective of +2. Strontium has a Z effective of +2, yes. So this is where our model breaks down a little bit, okay? So in actuality, the shielding gets less effective as the atom gets bigger, okay? So that's what you see here. So although the way we're calculating it, Z effective is the same, it's +2 for all of them, in actuality, Z effective increases a little bit going down the periodic table in the same group because shielding gets less effective. So Z effective goes up because shielding goes down as the atoms get bigger and bigger. Yes? So we are calculating the charge that an electron feels. So if we have a negative Z effective, if an electron feels a negative charge, where is it going to go? Out, yes. No, I don't think so. I don't think so. It still works. It still works. So why don't we do it for a transition metal? Let's do germanium. Let's do germanium. So again, writing out the entire electron configuration will help. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and then 4p2. Okay. It still works. Because without doing any calculations, germanium should have what Z effective? 4, +4. And it does. So where are the valence electrons? The 4s and the 4p. So we are thinking, what does those 4s and 4p electrons feel? So n equals 4. So what electron energy levels will we include in the shielding? 1, 2, 3. Do we include 4? No, we include 1, 2, and 3. So we include all of the electrons in this, and the 3D. Because 3 is there. Right? So it's not as, you can't do like germanium minus an argon shell. You also have to include those d electrons because they're included in, because n equals 3 for those d electrons. So you don't forget those d electrons. And you should get 4 because germanium is what, 32? So Z is 32 minus, I'm assuming if you count all of those electrons up, it should be 28. It should be, yeah, it should be argon plus 10, yeah, 28. So Z effective is 4 still. So this, don't forget those 3d electrons. for those elements that are heavier than gallium and germanium, those ones. So don't forget the Ds. Yeah.
So that means you won't necessarily look at the anomalous electron configuration like copper.
Wait, hold on. Can you repeat that again?
So like with the ones where you have to do like
The D block electrons. Let me think on that a little bit because D electron or transition metals always mess things up. Yeah. Okay. All right. So that will explain most of the trends that we'll see here. All right. So let's look at this series because in the next section we're going to look at predicting trends in atoms. So sizes. And ions, so size, atomic radii, and that forth. You'll have to be thinking about, energy levels of valence electrons as well as Z effective. So don't forget Z effective. All right, so let's look at this example. Let's compare how big a hydrogen atom is to a helium plus cation to a lithium 2 plus cation. The reason I want to talk about these three elements or these three ions is because all of them just contain one electron. You see that? Since of the charges, they all have one electron. So we're going to compare their sizes. So one way we can do that is by solving the Schrodinger equation. Do you want to do that? No, okay. So when you do solve the Schrodinger equation, you get radial probability graphs that look like this. So just looking at the graph, which ion is the smallest? Do we see? So remember how we read this, this axis R is kind of like the distance away that your electron lives away from the nucleus. All right, so that means lithium will be the smallest atom, or lithium 2 plus. Do we see that? Do we see that? Because it's squeezed in. Versus a hydrogen atom where the electron lives is spread out in a larger space. Okay, so I don't want to solve the Schrodinger equation. So instead we'll use Z effective. And it will tell us the same thing. So all of these substances, just a hydrogen atom has one electron. A helium plus cation has one electron. Because typically it has two, but we remove one, so it has one. A lithium atom, if we remove 2 electrons, so it's lithium 2 plus, has 1 electron. Right? So what's the Z effective for those 1 electrons that are orbiting the nucleus for all of those? So remember, Z effective equals Z minus S. So if there's 1 electron around the nucleus, is there any shielding? No, that electron is as close to the nucleus as it can be. So Z effective in this example is equal to, Z effective. S equals 0, we just said that. Shielding equals 0. So shielding equals 0. So for hydrogen, Z effective is equal to 1, because Z is 1. For helium, Z effective is 2, because it's a helium atom, there's 2 protons. Okay, now you got this one. Lithium is 3, and this is just for a lithium 2 plus, so there's only 1 electron orbiting it. And I'll show you why this explains this trend that we see, okay? So we just said that the hydrogen, that's +1, +2, +3. So if we draw the electron orbiting it, each of these examples, okay? And so what we just said, that this electron feels a Z effective for the hydrogen atom of a +1 charge. This electron on a helium plus cation feels a +2. This electron feels a +3. Because there's only 1 electron on all of them, right? So which electron, hydrogen, the helium cation, or the lithium cation, is the most attracted to the nucleus? Lithium. Which one's the smallest? Lithium. So we didn't have to solve the Schrodinger equation. Thank God, thank goodness. Okay. All right, so, all right, yeah, did we answer this? Which one is the smallest? Lithium 2 plus, because Z effective is the highest for that one. That the electron is the most attracted to the nucleus, so it will spend more time, or it'll spend more of its time closer to the nucleus. And the largest in this case will actually be, not helium, which is hydrogen, right? Because its Z effective is 1. Do we see that? Okay. All right. I think that's a good place to stop. So we will take these ideas. Don't forget about Z effective. We will be using it constantly for the rest of the chapter. Yeah. Let me just go back one slide. Yes.
You said that the
Oh.
x-axis is distance, but
This is probability. This is the same as a radial probability map or radial probability graph from chapter 6.
with the
Yeah, the things. Yeah, but in this case, since they're all in 1s orbitals, there's no nodes. Because if we have more nodes, like if we had a 4s orbital, you'd have 4 humps. You're trying to say, hey, your electron is spread out further from the nucleus.
And wait, what did you get from this? You could tell from this that lithium would be the lightest.
Not the lightest, the smallest.
The smallest.
Because the electrons are spending more time closer to the nucleus. Because 0, 0, that's the nucleus. Versus hydrogen, its electron will if you take a picture of it, you might find that electron out here in 5 and R5. Yeah. Yeah. What's up? See ya.
So last week, I didn't have time to show it
Okay.
to you earlier this week because
Yeah.
people had actually important things to talk about.
This is important too.
But